Hello and welcome back to Calculus 1, section 4.2 on mean value theorem. Mean as the average, not mean as evil. So let's put that first. Before we go into formulas, mathematics, and all of these things, let's first consider one scenario. So here I have a highway, 78 westbound, it doesn't matter. Here is your car. Let's add some tires over there. You want spoiler?
Yeah.
Why not? There we go. Alright, so you're going forward. Now, what I'm going to have here is some shrubbery. And we know what hides in the shrubbery. Or behind it. Kangaroos?
Yeah, kangaroos.
Let's see.
Oh, yeah. Those kangaroos.
All right. So this would be a speed trap number 1, measuring the speed in this region here. Now, obviously, as every speedster, you invested $400 into the latest radar detector, because when it goes off 2 or 3 times, it already paid itself off, right? So you are driving down the highway at 1700 miles per hour, and it goes beep beep, and you immediately reduce down to 60 because the posted speed limit is 60, and you pass through the gate through the trap at 60 miles per hour. Do you get pulled over? The answer is no, you don't, right? Drive few miles down the road, another shrubbery, another trap, tires obviously, and this one is measuring as well, and your trusty speed detector goes beep beep again, and you pass 60 through, and you drive off without being pulled over. Wait few days, there's a ticket in the mail. So do we have anyone who received the ticket of speeding in the mail without actually being pulled over in this room?
My mom did it.
There we go. Okay. So it's not in this room, but the mom. Okay. So what happened? Well, what happened is today's lecture. As you go through the first gate at 60, and you go through the second gate at 60, you don't get pulled over because you're driving the speed limit. However, if you're driving the distance, so I'm just going to get rid of these random lines and just go cop to cop. The distance is, let's say, 5 miles apart, and you cover this distance in 4 minutes, let's say. So what happens, right? Well, we have that the distance equals rate time, right? Which means that your velocity or speed is distance divided by time, which is 5 miles divided by 4 minutes. You are covering 5 miles per minute. Now we like miles per hour. So your 5 miles per minute in 4 minutes, is going to be multiplied by you want to kill minutes and you want to put hours. So 1 hour has 60 minutes. So now minute and minute cancels. This is a standard chemistry or physics conversion when you just convert the units. And what you have is 60 times 5, which is 300 over 4, which is 75. So your average speed between the two traps was 75, and the speed limit on the entire road is 60, so you are clocked at 15 over. Clocked at a 15 over is more than 14, right? So you are in that $200 range for a ticket. It's a violation 39-4-98, I think. There's a stack of those. No, I'm just kidding. So what you have here is the average. What we learned today is a formula for mean value theorem, which states that for continuous functions, where we have also that are differentiable, the average is equal to the derivative at least 1 point. Now, when you are stopped for speeding, you are stopped for instantaneous velocity, which is the derivative. The one that I calculated there is average. So those are two completely different concepts. But the theorem we are learning today is connecting these two, and the theorem says that if the function is continuous, you did not teleport along the way, right? And if it's differentiable, which means you were always driving at some velocity, that's a derivative of position, right? So both of those conditions are satisfied. This theorem guarantees that at least at 1 point, your instantaneous velocity and your average velocity are the same. Since the average velocity computed is 75, that means that at least once you were driving 75 as instantaneous and you get ticketed, which is why she got the ticket in the mail. Now, how do you implement this? Easily. Do you actually get all of these cop cars around line up? And then they say, okay, the red car was driving this one, the white cars weren't. No. You can either put the gates or just do it with Easy Pass.
Yeah.
Easy Pass gates are, and this was piloted for years now, so they're ready to roll it out at any point. Going to any Easy Pass, right? They should have this system in place. So now, what you go is, and you can't escape it. I mean, you can escape it, but you drive 120, and then before you go to the next gate, you park for about 3 minutes, right? And then you pass through the second gate. I mean, you can do that, to trick the system. But the idea, yeah, I know, it beats the purpose, right? So this is what is actually happening. Now, in all fairness to the whole process, right? Remember that 75 is your average speed. Remember that you had to slow down to pass through the second at 60. So if you had to slow down to pass through 60 and 75 was average, wasn't there also much higher speed so that 75 gets to be average? Well, at least you're not ticketed for that one, right? Because at that point it's going to be licensed and, I don't know, firstborn taken away or something. So let's take a look at the formula, right? What we call the mean value theorem. So we have, so this is a theorem. If function f is continuous and differentiable on interval AB, then there is at least one point C in AB such that the derivative computed at C is equal to f of B minus f of A divided by B minus A. So this is your formula, and you also have to have those conditions. Conditions of continuous and differentiable. You can't just disregard them, because if I am able to teleport, this is no longer valid, right? So what you have on the left-hand side is the derivative, which is instantaneous velocity, let's say. On the right-hand side, we obviously just a basic formula for slope, y2 minus y1 over x2 minus x1. So that's your average. And as I said, this is the one that we compute, right? We said this is how far you went in this time, and that being equal to this one, which was the one that you were ticketed for, and there's equal sign in between, so it's okay. So now let's calculate first just a random whatever problem, and then we'll do some word problems that will make sense. So let's say problem 26, find C where mean value theorem holds. So your job is to calculate C. The specs are function f of x is ln 2x, and the interval is 1 to e. All right. I need the derivative. So f prime of x is equal to what? Copy the function down, and then 2, and then cancel, so 1 over x. So if f prime of x is 1 over x, what's f prime of c? 1 over c. All I did is I replaced x with c. Perfect. What is my f of b, which is f of e? Is ln 2e. How much is that? Well, that's ln 2 plus ln e, which is 1 plus ln 2, right? ln e is 1, and ln 2 is just ln 2. How much is f of 1, which is f of a? It's ln of 2, which is just ln of 2. So now plug everything in the formula. The formula is f prime of c is equal to f of b minus f of a over b minus a. F of c is 1 over c. F of b is 1 plus ln 2 minus f of a is ln 2 divided by e minus 1. These guys drop, and we just have 1 over e minus 1. Now I need c, so if I flip left side, I flip the right side. So if 1 over c is equal to 1 over e minus 1, then c is equal to e minus 1. And that's what they were looking for. E is about 2.7, so about 1.7 is the value where the derivative equals to the average. Also, another way to think about this formula, I'll put this in, let's say, in blue, is that the m tangent is equal to the m secant line. If you are connecting this to the lecture 3.1 for when you learn the m tangent. Now that will, so f prime of c is equal to f of b minus f of a divided by b minus a, and me saying that m tangent is equal to m secant. If you consider a function with a tangent line and another from A to B, what we know is that two lines are parallel if their slopes are the same. So that will be graphical representation of what we are doing here. Let's calculate 30, and then we'll do word problems after this. So this is one of the, so for your third exam, this is one of the word problems you have. Problem 30. So what's C? F of x is x plus 1 over x, and the interval is 1 to 3. So derivative and plug in, all of this. Don't forget about the scholarship if you did not. If you are interested, take a picture. And all of you have Galileo, right? For STEM, scholarship for STEM, the Society for STEM. I think your GPA needs to be higher than 3 or 2.8 or 2.75 in STEM. No nursing, no business. Math, chemistry, physics, computer science, engineering of all kinds. You have 3 flavors, right? Chocolate, vanilla, and strawberry. What else? And is there anything else? So all STEM. It gets you minimum of 500 per semester. All the advising you need, and resume workshop, internship opportunities, Sanofi internship stuff, and a lot of other opportunities. So pursue that Galileo thing if you haven't so far, and you're staying for at least another year. You have to take 6 credits or more. So if you're taking less than 6 credits, you're not eligible. Yeah.
What?
0.9996. What do you like? What's it, cash?
I guess. You must have off the top of your head.
Cash is a mess. Alright, let's do this one so we can go and do some word problems and have fun. So, I need a derivative. It's 1 minus 1 over x squared. Are we all green on this? Beautiful. So I have 1 minus 1 over c squared is equal to f of b, that's 3 plus 1/3, minus 1 plus 1 over 1, divided by 3 minus 1. So original function plug in 3, minus original function plug in 1, divided by 3 minus 1. So 1 minus 1 over c squared is equal to 3 plus 1/3 minus 2 divided by 2. What do I have now? 1 minus 1 over c squared is equal to 3 minus 2 is 1. So 1/2 plus 1 over 6. That's times 3. So 1 minus 1 over c squared equals to, that's 4 over 6, 2/3, right? And then swap these two. So that's 1 minus 2/3 is equal to 1 over c squared. This is 1/3. So c squared is equal to 3. C is equal to plus minus root 3. Ta-da!
What does that answer mean? That just means
That's the x value.
2 There are two mean values.
There will be two values, yes. There will be two tangent lines that are parallel to this secant line. Now, since you asked, we are going to graph this in Desmos and find them. Which is awesome. Plus 1 divided by another x. And there they are. Oh wait, I have 1 to 3, so I have to kill the negative one. Oops. So c equals root 3 because we are on interval 1 to 4, 1 to 3. Okay, so let's see if I can work this out. I'm going to make this larger. It's not that great, but not that great of a problem, but we'll try. So from 1 to 3, so from this point to this point, there is a line, and this is secant. Your root 3 is approximately 1.73, so 1.73 somewhere here, so that will be there, and the tangent line that you get to draw to this point, terrible, should be parallel to the other one. Where's the microfiber cloth? There. Terrible.
The curve confuses the word.
Sorry?
The curve is kind of interfering with the tangent lines.
Yeah. So we have M tangent, which is a tangent line, and M secant, which is a secant line. And these lines are parallel. So at this point here, right, where the curvature is perpendicular to the line, and we know what the tangent line is, they're parallel. Okay. Let's take a look at word problems. I know you are all waiting for that. Enough of this pointless flexing, right? Let's do word problems. Lapse rates in atmosphere, drag racer acceleration, obviously. The fastest drag racers can reach a speed of 330 miles per hour. This is problem 20 in the book. Over a quarter-mile strip, in 4.45 seconds from a standing start. Complete the following sentence about such a drag racer. At some point during the race, the maximum acceleration of the drag racer is at least miles per hour per second. So acceleration is at least something miles per hour per second. Well, if your speed is 330 miles per hour and you started from 0 and your acceleration is velocity over time, your speed was 0 to 330, meaning that you are constantly accelerating. So there you A and B, and you have the time t of 4.45 seconds in which that occurred. So you have your so you have your 330 minus 0 divided by 4.45, which is 330 divided by 4.45. Let's see, abacus. .2. Oh, we had the 2 decimals there, so we can use 16 miles per hour per second. So they gave you that your start velocity is 0. Right? Because the car before the race, right, you stand still, and then when the green comes up, everyone launches into a race. So your start velocity is 0 until you push gas pedal. You drove straight, it's a drag racer, right? You drive straight, quarter mile, and the highest speed you hit is 330. So to find the average, it's 330 minus 0, because your A speed was 0, your B speed, the final speed is 330. So 330 minus 0 divided by the time it took you. Now they want our answer in, for whatever reason, in miles per hour per second. So it's, when you divide, simply 74.16. We already did a police problem. I'm laughing because problem 43 says mean value theorem and the police. And then the problem 44 says mean value theorem and the police again. And I'm not joking. So if you open the book, you'll see that. They do that all the time. We can talk about running pace. Explain why if runner completes a 6.2 mile race in 32 minutes, then he must have running exactly at 11 miles per hour at least twice in a race. That's a cool problem. Explain why if a runner completes 6.2 mile race in 32 minutes, then he must have been running exactly 11 miles per hour twice. This is problem 45, running pace. Well, it's more of the same. If you are running from point A to point B, you started at distance equals 0 to a distance of 6.2, and the time it took is 32 minutes. So we have the same 6.2 minus 0 divided by 32 but it's 32 minutes, not hours. So I have to put 6.2 miles divided by 32 minutes, and then I have to get rid of minutes and leave hours. So 1 hour has 60 minutes. So now you have 6.2 times 60 divided by 32 to get 11.625 miles per hour. Now look, you started with 0 velocity and then you went to 11.625, which is more than 11 that they are looking for. So wouldn't you agree that if you're, let's draw a velocity graph. Velocity graph is, you start running with the velocity, this is in time, you start running with the velocity at 0 because you are in that position on the ground before the gun goes off, right? When you start running, your velocity goes up and goes up and goes up, and then let's say you get tired and then you end the race and you stop. If this is the level where you had 11 miles per hour, because this peak over here is, let's say, 11.625, you had to pass 11 to get to 11.625, to go back to 11, to go back to 0.
Why can't he be like a drag racer and continually accelerate? Or she?
Because you have to stop. Right? The drag racer gave us their top speed, right? The drag racer had the top speed. The drag racer actually stopped eventually as well, right?
But after the finish line.
Yes.
The runner can't do that. Anyway.
They can, but I mean,
Two humans though. So
the boat, no, but the boat work, right? The drag racer, if you ask me how many times drag racer hit 100 miles per hour, I'll say guaranteed twice, right? Once to accelerate over it and one to decelerate to stop. Now, can drag racer, obviously they are not going to, but can drag racer do this with a speed? Yeah, right? Hit 330, slow down to 100, hit 330, slow down to 100, right? I mean, this is the way you drive. If you stop on stop signs and traffic lights, right? Those are not suggested, they're mandatory. So your speed goes up and down all the time. So the idea is that you will surpass 11 to a higher speed, and then you would go down through the 11 again, eventually to get to 0. Now, right, you go running, and then you get tired, and then you get motivated because someone is catching up with you, right? So you can do all of these things, and then eventually you'll have to stop. Maybe you just stop like this after the run is over. So I don't know how many times I hit 11, but I'm guaranteed to surpass it once, and then to slow down once on my way to, actually this would be a much better right here. So I'm guaranteed to pass 11 once and then to stop. Now what happened in between, right, the fluctuation. Also can discuss this as you push an object, right? You push an object, use your strength, right? And then as you're getting tired, there's less and less force pushing because you are tired. You're still pushing, but you're not pushing as much as when you were rested and pumped to actually push something in the beginning. So the graph, right, would be you start at 0, you make a contact, you push, and then, right, it starts to wear off. So those are the word problems. I have to worry about one of these. Bye.